Today, I wanted to take a step back and explain some of the parameters that you can set when you use the LLM API, such as the temperature, top P, top K, random seed, and how they impact the response that you are getting back from the model. Just for you to know, we are going to simplify, of course, some of the concepts, so it's easier to understand. And the main one is that we will pretend that a token is a word. We completely disregard the tokenization process. With that in mind, it means that we've got a neural network. The inputs are different words, like coding is very, and then you expect your LLM to predict what is the likely next word in your sentence. And it will do this iteratively until it can produce the entire text for you. In that case, we can see that it has output different words. Of course, some fictive examples like fun, useful, frustrating, banana, blue, and each score has an associated so-called logit, which is a likelihood score to be the next word in the sequence of words. So these are not really a probability distribution yet because these scores are not constrained to a range. They are not between 0 and 1, and the sum of all these logits is also not between 0 and 1. They don't add up to 100%. However, this is going to be one step in the process, is later we will convert these logits into a probability distribution. What is similar, however, to probabilities is that the higher the logit, the more fitting the word is to be the next one in the sentence. So here we've got our inputs, as we said, and the output in reality, it will be one score for each existing word in the vocabulary of your LLM. So if your LLM has a complete vocabulary of 100,000 words, it will also produce 100,000 logits. So one for each word in its vocabulary. Of course, we didn't want to go through this entire process for this example, so I just chose here for the illustration 5 words. And here, when I start creating my arrays in NumPy, I chose 10 words. So it should be enough for us to be able to go through the different examples and to see how it works with some illustrations, charts, tables, and code samples, of course. So let's just create these two arrays. One contains the words, one contains the logits. The first thing that we are going to do, and this is before we convert the logits to the probability distribution, we are going to scale these logits. So each logit will be divided by a temperature setting. And the result of this is that if you use a very high temperature, like 1.5, or a very low, like 0.2, you will either flatten the curve or sharpen the curve. So you will increase or decrease the difference between the logits. And why would you do that? It's if you want more creativity, you will want to flatten the curve to decrease these differences between the logits because you want in the next step when you will filter out the less likely words that they still have a likely a fighting chance. However, if you want something more deterministic, you want really to increase this difference between the logits, so the most likely words will be the one that you will pick in the next filtering step. So it's really up to you, depending on what you want to achieve. Probably wouldn't recommend a high temperature like 1.5, which is often the maximum that the model can handle, because you are also more subject to hallucination when the LLM gets more creative. However, low temperature, on the other hand, may be suitable in some cases, not in some other. So you will use it, for example, for functions coding, where you want something more deterministic. However, you will not use it for some creative writing. If the temperature is 0, it's even different because we said that we divide the logit by the temperature, and mathematically it's impossible to divide by 0. So in that case, there is an exception handled by the LLM pipeline, and it will just pick directly the highest logit. So it will not go through the further steps that we will discuss in this notebook. And in our example, it will just take the word fun because it has the highest logit. That's why it is more deterministic, because it ignores a lot of the steps after with some randomness. It just picks the most likely one here. A few samples here from the Mistral documentation. explaining a bit more how they use this temperature or how they recommend you to use it. So the range between 0 and 0.7, this is the recommended one. However, for most of the model, you can go up to 1.5 if you wish so. They also tell you that um, the default temperature is not really in their documentation, but you can call the model's endpoint if you want to retrieve it. This is what we are going to do in the next cell below. They also explain why a temperature of 0 is not 100% deterministic, and there can be some slight differences if you try to replay the same sequence. And you can just read this paragraph if you're interested in this topic. Let's have a look first at the default temperature for a given model. So as we did in some previous videos, I just create a Mistral client, and after that I'm calling their model's endpoint as they suggested, and I'm retrieving one model. So I chose Mistral Small Latest, the one I'm using the most in my videos. And once I retrieve this model, I can just query the default model temperature. And we see that in that case, it's 0.3, and it's not really surprising because they don't want the model to be fully deterministic. Otherwise, it wouldn't be able to handle many situations. However, you also don't want it to be too creative because it will be subject to the hallucination. So 0.3 is usually quite a good balance, and you see that it's more or less in the middle of the range that they recommend, between 0 and 0.7. But then it's up to you, depending on your use case, to adjust this setting. What I'm doing here next is that I will show you actually the prediction for the two extreme temperatures. So we can choose the temperature 0 and we can choose the temperature 1.5 and ask exactly the same question in both cases. So I'm using Mistral Small Latest. I put maximum tokens 5 because I want a very short output. I'm actually asking to get a single word in the system prompt. The temperature will be one of these two in the loop. So the first time in the loop, it will use 0. The second time, it will use 1.5. And something that we haven't seen so far, but there is an n parameter in the completion method that you can use to generate more than one completion at a time. So for each temperature, I want 10 completions, so I can see how each completion will differ from each other. So this type of randomness in the model. So I call 10 times the completion for each temperature, and then I just display them. Let's have a look. We see that at temperature 0, this is really deterministic. It always picks the most likely word. So it was the word fun. However, when we use the highest temperature possible, 1.5, this is much more creative, and you see that it has a lot of different words: useful, fun, fascinating, hard, interesting, intense, and so on. So this is really the difference between the two, from the most deterministic to the most creative. But this is not the end of the process here. So this is just how we use the temperature, but we need to see how it fits in the entire pipeline. So we say that the temperature is used to scale the logit before we turn them into probabilities. So I'm still using these 10 words and their logits, and all these logits will go through the Softmax function. You can see here the formula, the exponent of the logit over the sum of all exponents of logits. And this is how, if you give a vector of these logits, you will get then the probability distributions. So all these probabilities will add up to 100%. Here I've asked a LLM to generate some code for me because I'm very bad with matplotlib to create the charts, but I wanted to display visually how different settings will change the probabilities. So I kept 3 scenarios. So a low temperature, what is called here normal, I should have called actually medium, and high temperature. So we've got 0, 2, 1, and 1.5. And you see that in each case, as we said, the logits are divided by the temperature. So in that case by 0.2, here the logits by 1, here the logits by 1.5. And these scaled logits are going through the softmax function to create the probabilities. And then we just want to display them on the chart. And this is what we end up with. So in blue, this is the low temperature, in gray, this is the medium one, and in orange red, this is the highest one. And you see that when the temperature is extremely low, the word fun has almost 100% probability to be the next word. We'll see later in the table, it's, I think, 99.9%. So then the rest is so small that we cannot see the other words. However, when you increase the temperature, then this word is getting less and less likely to be the next one. So from nearly 100%, it goes to 60 something percent, and then here, this is slightly under 50%. For the other words that were less likely with a low temperature, or nearly zero actually, when the more you increase the temperature, you see that the more it increases their probabilities. So here you get a small bump for useful, rewarding, frustrating, hard, and so on. So it will give them a bit more chance to be picked in the next step after we apply some filtering. And here this is just a visual way of seeing these 10 words, but we can also display it in a table. Sometimes it's easier to read, and we see that indeed with a low temperature, fun was almost at 100%, and then we had these two that were at 006, 002, and the other ones were just probably some rounding errors. But when we just round to two decimal places, they are at 0%. However, with higher temperature, let's look at the highest, for example, fun was just under 50%, and useful went from almost 0% to 18%. So this is how, if we summarized, we got the logits from the neural network, we scaled them with the temperature, and then we turned them to probabilities with the softmax function. The next step, the top K and top P, this is filtering. So now we want to select a pool of words that the LLM will be able to choose from. So we are not going to choose the most likely every single time, but we will do some weighted sampling in the last step from a pool of candidates. And to create this pool of candidates, we are using different techniques. It can be top K, it can be top P, for example. So in the option A, top K, it's very simple. K is a number of words that you want to keep, and you are going through the sorted list from the most likely to the least likely. So if K is 5, it means that you will pick the 5 most likely words. So I will maybe not take this low temperature because we don't even see if they are more than 0%. But high temperature, here you will pick, for example, so actually they are all sorted, but you will pick fun, useful, rewarding, frustrating, and hard because you say that K is equal to 5. So these are your 5 most likely words in the order of probabilities. The issue with this approach is that in some cases, like for example, here with the low temperature, so if we will look at all the digits, we will still pick these 5 words. However, some have so low probability that it's almost impossible that they are a good fit to be the next word. Especially if you will increase top K maybe to 10, 15, and so on, you could end up in that case with some words like banana, blue, that makes absolutely no sense. So it's not always a good approach to choose a fixed number of words. And because of this limitation, you will see that a lot of LLM providers don't even expose this parameter to you. If you look at Mistral AI, for example, their chat completion endpoint, you are not allowed to set this parameter. So a better approach in that case could be the top P, which will look in that case at a cumulative probability for the different words. So if you set, so you will need to set P between 0 and 1, let's say 90%, which is a default value for a lot of LLMs. And if you will set 90% in that case, you will just go from the most likely to the least likely, and you will stop when you reach the 90%. In that case, you will choose fun, that has a likelihood of a probability of 49%, then you could still add useful, you could still add rewarding, and I think here you will be at the 19%, so you will stop here with these 3 words which are extremely likely. So let's have a look with some code. The first one, this first code sample, what I wanted to show you, it's why the LLM providers like Mistral often don't recommend you to set both a top p-value and a temperature. So I chose the maximum temperature from the last time, 1.5, where we got very creative outputs. And I tried with two extreme top p-values. So one where we keep only the top 10% probabilities, and one where we keep actually the entire list of words, because if top p is 1, it means 100%, so we select all the words. And in that case, I just generate 5 completions for each, and it should be enough for us to see how a very low top p will neutralize actually the high temperature. And here we can see that, yeah, indeed, top p01, we get every single time the same word. And that makes sense because if you remember, with this temperature of 1.5, so assuming that they have the same list of words, but you see that if you end up with this type of probability, so top 10% will stop at the first word fun because it's already higher than this threshold. So here you removed all the creativity from the temperature because you are sampling only one word. However, if you would take 100% of the possible words, in that case, of course, you are still keeping a lot of creativity from your model. So here you get a lot of different words, and some that can fit and some that are not fitting at all. So here we can also simulate the top P on our list of 10 words. I started here with the balance temperature, the one that was set at 1, and I just divided again by 100% to have the probabilities. And here I'm just going through the different steps that we discussed. First to sort the list, and then to check where the threshold is reached, to extract the indices up to that threshold, and then you need to renormalize the different probabilities, because once you get these few words that, for example, are going to represent the top 90%, so then you need to renormalize to add up to 100% again. And after that, we can just display these new VIPs. So if we apply a top P of 90%, we see that, as we expected, when we went through the list manually, we are keeping 3 words, and we've recalculated the probability. So fun was at nearly 50%. So now that we have only 3 words, the new probability is 71%, useful is almost 16, and rewarding is almost 13%. So this is our final list of candidates to go to the last step, which will be the weighted sampling. So once again, here we are not going to pick the most likely word from the pool, otherwise we didn't need so many steps. It was quite easy to determine it. Here, what we will do, it's a weighted sampling. So still, even if it's less likely that we choose the word useful in wording because the probabilities are lower than fun, they still have a fighting chance in this spinning wheel. So what we are doing here is we just operate in the loop. So we want to see if we spin the wheel 20 times, what word will be chosen. What we expect here is that fun will be picked most often. However, I think in 20 times we should see a few times useful or rewarding. So you see that here we just choose from NumPy the random function, and we pass our 3 words here, and here we also provide the weight to do this weighted sampling. And indeed, most of the time it's fun, even many times in a row, and 2 times it was useful, and we see that here 20 times was not enough to pick rewarding, but if we would run it another time, most probably it would be here. It's still useful and fun, so rewarding, it's hard to get, but yeah, the 3rd time I run it, we still see that fun is pretty most often. However, sometimes you also pick rewarding or useful, and this is how you get some varied output from your LLM, and that it can create some interesting responses, and that's something which is very deterministic all the time. Actually, if you would be too deterministic, you wouldn't be able to solve any complicated problems. If you want something which is reproducible and you want to remove the randomness from the sampling, you can also set a so-called random seed. It's just a number that you pick and that you set before you do the sampling, and in that case it will always output the same choice. And after you have done it these 20 times, if you want to continue and reset, so you can remove here the random seed with none. And when you run it, you see that indeed we chose fun 20 times, because here we remove the randomness, so it will always pick the same word. And that's everything you need to know at a high level when you're working with your LLM client and you want to tinker with some of the parameters like temperature, top P, yes, top K, not often, it's not often exposed, and the random seed. This is how you can have different trials and see what fits best to your use case. Maybe the next video that we could do on the topic would be the tokenization, so we can have a look at the process before and we can remove this simplification and really talk in terms of tokens instead of word. But really the explanation, how we are scaling these logits, how we turn them to probabilities, we filter them, and then you do the weighting sampling, is exactly the same whether you are working with tokens or words. So that was probably a much needed simplification for a beginner introduction to these topics, but later I think we could talk about this tokenization again, and I hope to see you in that video in that case. Bye bye.